Okay, we are now going to understand and focus on this file called cppdefs.h, which is used to configure your ROM's application. In other words, this particular file contains the directives and instructions of which portions of the Fortran source code you want to retain in order to configure your particular application. This file is contained in the directory include, and so let's go and look in this directory. We do ls, actually we do l. So here's the cppdef.h file. But before looking into this file, let's just provide an example of how these directives can be useful. So for example, let's open a simple Fortran source code. So this is a simple source code of Fortran. Has a main program. It has some definitions of some variables. Then it has a first part of the program that is initialization. This could be your fake, for example, ocean model. And then here I have two blocks of code. The first block is the second order advection scheme, and the second block is the third order advection scheme. So if this was your ocean model, and then you would have other statements and so forth, you may just want to not use both advection schemes, right? You want to select just one type of advection, maybe the second order or the third order. So how can you do that without destroying your Fortran source code? Of course, the most unoriginal way would be to just create two files, one that has the second order advection scheme and the other one has the third advection scheme, and then use the appropriate file every time you compile. But if you think that in principle you have so many choices to make when you configure an ocean modeling application, you would end up with a huge amount of files. So it's very inconvenient. Another way to do this is to use the so-called preprocessor instructions, or directives, I should say. And these work in the following way. For example, I can say that I want to use either this block or this other block. So the way that these instructions work, these preprocessor instructions, typically they begin with a pound key. And then here I'm going to say if defined, say advection, let's say second order. Okay. Then I want to keep this block of the code, and so I'm going to just enclose this block of the code between these two statements that begin with the pound key, which is an if statement, if defined this directive, otherwise, and then there's the end if. Alternatively, I can decide to do the same for this particular directive. So I'm going to say if defined advection, in this case underscore third order. Okay, and I go down here and I close my if statement. Okay, so now I have introduced some pre-processing definitions. The first one is second order advection, and the other one is third order advection. Now how do I choose which one of the two I want to use? Well, at the very top of the program I can define the option that I want to use. In this case I prefer to use the second order advection, and I'm going to undefine the one that I don't want to use, which is this one. Okay, and so with this in mind now, I still retain my Fortran code with all the various advection schemes and so forth, but now through these definitions, when I start to compile this code, I can choose which of these two sections of code I want to retain. So in this particular case I define this, and so I'm going to retain the second order advection and remove the third order. So when you compile, typically what happens is that the compiler script will run a command that looks a lot like this, which is cpp, which is the pre-processing compiler. It's not the actual compiler, just prepares the Fortran code. And so for example, if I now save this and I execute that string cpp-p traditional, and I apply it to this Fortran code, what you find in fact that it strips out all the stuff that you don't want from the code. So here only retain the second order advection scheme, and if I do this, apply this command and I redirect the output, for example, onto a small F90 code, okay, and then I open the small F90 code, I basically have now a new version of the code that is stripped of all the things that I don't want to keep. So this is very convenient because you can foresee how such a logic can be used to maintain a very articulate code with a whole bunch of options inside, and then turn them on or off by just defining these particular options. So for example, now I can undefine this option and I can define this one. Okay, and if I reprocess this code, okay, you'll see that I will have retained now the third order advection. Okay, so this works. So given this very simple example, then we can look now at the cppdefs file that ROMs uses, which is cppdef.h, and in particular, even though this is the .h file is the one that we're going to use when we compile, I want to show you the original version of this, since I already edited this one particular. And if we look at this original version and we just go a little bit, we scroll down, what you see is that here you have a whole bunch of definitions or directives. They're all by default undefined. So then what you do, you go through these things, and for example, if you go further down, these are directives that are relative to the equation, to the momentum equations. And so for example, uv_advection here turns on or off the nonlinear advection terms of the equations. uv_core, turns on or off the Coriolis term, and so forth. Here you have different types of advection schemes and types of horizontal mixing and so forth. So all these are undefined by default. So if you want to retain certain dynamics, like for example the Coriolis, what you do is you just take this particular definition here, and you just change this to be to be defined. And so like this, when the model compiles, it will retain this option. However, these particular listings here are more here for your information to know what the available options are, and there's a lot of them, so that you can have all types of flavors of your ocean models. Typically, I like to have a stripped down version of this file that retains only the directives that I want to keep, and so this is my cppdefs file for an example that does Coriolis, or the initial oscillations. And so I define Coriolis here, and so if define Coriolis, which it is, then there's all these options that are enabled, or these directives. So I define the solve 3D, the UV advection, which is the solve 3D refers to the fact that you're solving the three-dimensional equations. UV advection is the advection terms of the equation. UV Coriolis retains the Coriolis terms. UV L drag is a parameterization for the bottom boundary condition, in this case a linear drag coefficient. EW periodic and NS periodic stands for periodic boundary condition in the east-west direction, north-south direction, so this would be a doubly periodic domain. And then there's a whole bunch of other options that commence with ANA_, and these are referred to the fact that I'm running an analytical case, the Coriolis inertial oscillations, and so I'm providing in the source code the grid configuration parameters, the initial condition. All these other options are, for example, for for surface and bottom boundary conditions. This is for mixing, and this particular option, floats, stands for the fact that I want to enable some synthetic floats in the model to track particle trajectories, which is kind of cool in the Coriolis, because the initial oscillation, you'll find that particles undergo circular trajectories associated with the inertial motions. So this is just one example, and again, here I just stripped down the ones that I want to keep, and if you don't know what these are, you can always quit from here and open the cppdefs.org file, for example, .h/org, and you can look, for example, say for solve 3D, which is one of the option, and you can get you can understand what this option is used for. Once again, when you first start pre-processing the source code using these definitions, they're all by default undefined. So that's why you need to have at least a very basic sets of definitions like the ones presented here. So this actually is enough definitions to run this Coriolis application, which is one of the examples of the training. So this is all about the cppdef file, and in principle this is all you need to know in order to configure your ROM's application, although there are certain other parameters that you need to do, which we'll see in the next sections.